Welcome back to the classroom. My name is Mr. Wong. We're just following through our second part of the lesson, which is on motion in gravitational fields, and we are trying to predict the gravitational field strength of an object near the center of a planet. Now, before we begin, let's just quickly talk about a thing called non-contact forces, which we would have originally talked about in stage 4, so year 7, year 8. And where we talked about forces, non-contact means it's an interaction facilitated by a field. What we mean by a field, it is a region of space, or a region of anything really, where we have some kind of value to measure how strong or how tall or how long something is. The best example is when you see the tomographic graphs. So you can see like the different mountain tops, and you can see like, oh, at here it's 500 meters. Then if we go further along here, this is 200 meters. So that's kind of the idea there. So there's three types of fields that we would talk about. One is the electric field, where we talk about the interaction with charged particles. If you recall, the symbol for electric field strength is E. We talk about magnetic fields with magnetic objects. We don't talk about this one here, but it's used capital B as the example. That comes in module 6 when we look at electromagnetism. And the one we're looking at today is gravitational fields, which is the interaction of mass objects with each other. And that is given as G. Okay. So what I want to firstly show you is if you look at this diagram here, it follows the same idea when we talk about electric fields and magnetic fields. You can see how the field lines are denser, so more packed towards the center here. So as we go towards the center like so, you can see the arrow, the vector arrow showing the strength of the field gets larger. As we go further away, you can see that the field lines are more spread apart, so low in density. And so it also means a lower gravitational field strength. So just remember this, when we draw these gravitational field lines, the direction of our arrows will tell us the direction of the gravitational fields. The density of the arrows tell us the strength. High density means a strong field. Low density, here, means a weak field. And if we really narrow down, so say for example, I go and take a really quick snapshot of one particular surface, a really small surface of Earth, where it kind of looks quite flat. The lines look a bit more uniform. If it's uniform, parallel, it means that we have a relatively similar gravitational strength. Obviously, it does vary, and we'll talk about that in our later episodes and lessons. So, just a quick multiple choice quiz for you. 2 questions. What is a gravitational field? Which statement about the weight of an object is correct? I'll give you 5 seconds to just quickly pause this video before I go into the answer. So I'll start my count now. Okay, so what is a gravitational field? Well, a gravitational field is the region in which a mass experiences a force. A region being an area where there is some kind of value, and we know that gravity interacts with mass objects, at the very least using Newton's formula of gravity. And then, which statement about weight of an object is correct? The answer is 0. So if the gravitational acceleration is 0, our weight force is also 0. This actually aligns with Newton's second law of motion. So Fg equals to m times g. If g is 0, then by the calculations or normal arithmetics, we know that this would have to be 0 as well. Okay, so Let's talk about Newton's second law. We can actually use that to calculate the acceleration due to gravity, because if we know the weight force on an object and we know its mass, we can do the division and we'll find little g here. Little g meaning the average of the acceleration on Earth. Now this is obviously an average that we look at all the different components. So this is just the little average we have here. So how could we actually work out precisely the magnitude of the gravitational acceleration for each object? Okay, the reason why we want to look at that is we talked about this before. Different regions of Earth have a different, distance from the center. So if it has a different distance, then the acceleration due to gravity at those points would be quite different to each other. Okay, and we're not really looking at the little masses. What's happening is in that original equation, we're looking at the acceleration that this little mass experiences, but we're not actually looking at the bigger mass, because it's actually the bigger mass that causes the acceleration. It causes the gravitational attraction. So we want to look at it from the perspective of the larger object, and we also want to take into account the distance between where the objects are. Okay, so we're going to try and equate weight force and gravitational force together, because they are the same thing. When I say weight force, it's due to a gravitational attraction. And what happens is I can rewrite this equation into this equation here. Okay, assuming that little m represents the smaller object, they will cancel each other out, and I'm left with this formula here. Remember, this formula is to represent the fact that on Earth we have different heights. If we're on Mount Everest, if we're at the bottom of the seabed, and we're trying to look at the perspective of the planet. So that's what we're trying to look at here. Okay, and that gives us G. Okay, so this is the value that we have here. It is a magnitude of vector proportional to the object's mass and inversely proportional squared to its radius. Essentially, this has a direction as well as a magnitude. It is a vector. So keep that in mind. So obviously, now that we've talked about that, the last thing we need to actually do is to work out what the acceleration due to gravity on Earth is. And the values we're going to be using is the mass of Earth according to our data sheet, and also the average radius on Earth. So we're not really taking into consideration different specific points like the ocean bed or like Mount Everest type height. We're just looking at, on average, what is the average acceleration. So what we can do, obviously, if we equate the equations like we talked about before, we subtract the object, because the reason why we can cancel out is obviously if the object is very small, the acceleration they cause is also going to be very small. So you can do it the other way if you want to work out how much acceleration we put on the Earth, but that's not necessary here. So that's the equation we have. If we do our substitution using the values given to us, we get 9.81 meters per second squared. Do remember though, you need to convert your kilometers into meters in order to match the same units as prescribed by the big G constant. So that's actually how we work out the average acceleration on Earth. Just a little bonus for you. We actually use gravity to help us find extrasolar planets. So planets that orbit around stars, also exoplanets, similar to ours, we know that when a large planet orbits a star, it causes the star to wobble in a way. The star's appearance will vary. These variations in brightness can be detected on Earth, and that's actually how we can, or how one of the methods can be used to discover exoplanets. These are the different types of exoplanets that we've found at this point now. So there's an application for you. Okay, and so this concludes the second part of our lesson here. First part, we talked about Newton's law of universal gravitation. And our second part is to work out the gravitational field near a point mass or spherical object. Okay, I'm Mr. Wong. Thank you for joining. And if you thought this video was helpful, give it a like, subscribe if you haven't done so already, and I'll see you next time.